Hi, good morning, everyone. Can Santosh, you confirm that my screen is still visible properly and audio is fine?
It's visible, Neeraj.
Okay, great. Thanks. So, good morning, friends. I have two lectures with you today, and what we are going to do is to have a quick overview of interstellar medium of galaxies, and in that particularly, I'll focus on why we are interested in looking at the atomic phase of ISM, and for this, I will cover both the observational aspects of it. That is, in the first lecture today, we will try to understand how is it that we can probe, look at neutral hydrogen in galaxies. And in the second part, which is in the afternoon, we will see what is it that we can astrophysically learn from looking at neutral hydrogen in galaxies. Right. So that's the basic plan, like clearly split between these two lectures. So first, let us try to understand that what is it that we are looking at when we are talking about interstellar medium in galaxies, and how does it relate to, in particular, the neutral hydrogen ISM. So most of you, and especially those who do amateur astronomy and have looked at sky with even simple binoculars, not even telescopes, would have looked at Orion Nebula. It's one of the nearest star forming regions to us, and in that even with a simple binocular you can appreciate the beauty of this image, but also at the same time the kind of complexity that it presents. For example, the image presented here is from Hubble Space Telescope. It's a space-based telescope providing the best resolution of this nebula, and you can see that in this nebula we see not only these very bright star forming regions, but also there are these dust lanes or dark patches where we can infer that there's a lot of molecular gas that the stars are forming. So you can imagine that when these stars are present or when they are just formed, they will emit photons of high energy, especially if they are of energy greater than 13.6 electron volt. Then in that case, they would actually also ionize the hydrogen around it, right? And the size of those H2 regions or the ionized regions around stars is like few parsecs, right? And the kind of molecular clouds that we are looking at in this picture can run from tens of parsecs to few hundred parsec, right? Especially the kind of molecular clouds we call as giant molecular clouds, they can be as large as few hundred parsec. So when such as in such a cloud, there are these pockets where stars are forming, and it's very well understood now that when stars form, they primarily form from molecular gas. That is because it's only in those regions of the clouds or in the galaxy that gas can cool down and collapse to densities which are high enough to form stars, right? So that the fusion can start. So one thing that we have to clearly understand and appreciate is that it's the molecular gas which is the uh, direct fuel for star formation. But even before we can form molecular gas, it exists in atomic phase, and that's what we are going to focus today. Like that, what is it that how is it distributed in our galaxy, Milky Way? How is it distributed in the external galaxies? Then how and in what conditions it can actually channelize to form molecular gas and then can be converted into stars. And of course, as I implicitly mentioned a short while ago, that the moment stars are formed, they will actually ionize neutral hydrogen around it and even destroy the molecules in that process. So there is this complex interplay which takes place in interstellar medium, in which all these different interfaces are linked to each other, and we will look at what we do with the neutral hydrogen. So when we say look at in our galaxy Milky Way, which has got about 10 to the power 11 stars, right? So there are a lot of stars in our galaxy. They are distributed over a disk of approximately diameter of 10 to the 5 light years. And if we just try to estimate what is the nearest neighbor distance between these, we find that it is of the order of few parsecs. So this implies that in our even within our galaxy, when which has got so many stars, and we look at it in the sky, there's a lot of empty space in between them, and this empty space is not really empty. It's actually filled with a lot of gas, and that's what we refer to as the interstellar medium. And it has got these following components. When we talk about gas, it can be molecular phase, which we saw like is a direct fuel for star formation. Then it can be an atomic phase, which is what we will focus on the rest of the talk, and then it can of course be ionized as well. And then in addition to these gas phases, we have got dust, we have got cosmic rays, which are high energy relativistic electrons. And then also we have to consider that there is a lot of radiation field and magnetic fields present in the interstellar medium, and they play a very crucial role uh, in the formation of stars from molecular clouds, and also they are important for the physical processes through which we can observe different components of ISM. For example, in different lectures, you would have come across that we can look at a non-thermal emission, which is essentially the electrons going around the magnetic fields present in the galaxy. So that's the synchrotron emission, which sort of shows us where this plasma and magnetic fields are present in the galaxy. So to conclude from this, that there is this vast empty space between stars, but it's not really empty. It's filled with what we call as interstellar medium. It has got these different components. Right. So, a short digression before we go into atomic phase. You may wonder, like, how do we actually really learn about that there is something in between stars? So this was almost 100 years ago. It happened. Uh, uh, the discovery of ISM, because prior to that, people knew that there exist these stars in our galaxy. But Jonas Hartmann, in 1904, he was observing uh, a star, Delta Orionis, and it's actually not a single star, it's a binary star. It's in the Orion constellation. And he found that there are certain set of absorption lines in the spectra of this star, and these are absorption lines actually arising from the stellar atmosphere. And since this is a binary star in which it's going around the center of mass of the system, these absorption lines periodically they get red shifted and blue shifted depending on as the star is moving towards or moving away from us, right? So that's the motion that is taking place. But in addition to these various absorption lines, they identified a particular set of absorption lines which corresponded to calcium doublet, which means that it's a set of two absorption lines which did not share this periodic motion. So this was a clear indication that it is arising from gas which is not associated with the star, but it is between star and us. And the most probable place was that it's actually coming from the interstellar medium of our galaxy. So this is how, in very early days, like more than 120 years ago, it was realized that there is interstellar medium present in the galaxy. And then, of course, it's not just the presence of something, but we can also infer the presence of interstellar medium from the absence of light. And what we are seeing in this image, Bernard 68 cloud at different wavelengths. So if you see the most uh, in that top left corner, we have an image at 0.44 micron. And as we go progressively, we are having images at longer wavelength. It's the same patch of the sky we are looking at. So we go in clockwise direction. And you see that like the wavelength of these, as the wavelength of these images is increasing, the patch which was appearing very dark at initial ultraviolet and very short optical wavelengths actually is actually filled with stars when we go into infrared. So what was happening here is that there is this dark cloud or the molecular cloud present here, which has got a lot of dust associated with it, and this dust is actually preventing light from short wavelength light coming to us. This is obscuring it. So this was another way through which it was discovered that there is actually a lot of material between space between stars. Another component of interstellar medium. This was detected in mid 20s, right? So why study ISM? Why study any phase of gas in general? Because gas is where it all starts and ends. If we want to understand evolution of galaxies, which an evolution of galaxies is nothing but like how it converts gas present in it to stars and how it interacts with its ambient medium. These two things then influence the stellar composition of the galaxy, and will also influence of what type it looks like, whether it has a prominent disk or it has a disk and bulge or it only has a bulge component, right? So these are the different processes that would determine. And stars from the ISM, and as stars from they also enrich the ISM, because eventually they will die, they will go into supernova, and even before that they will also emit a lot of radiation. So there's a lot of radiative and mechanical feedback processes that also leads to energy input into ISM. And all these things determines the properties and evolutions of galaxies, right? So this is the famous tuning fork diagram, which I'm sure all of you are familiar with. This is what I was referring to, that there are these various physical processes through which a galaxy may evolve from one form to the other. On the left hand, we have early type galaxies, which are primarily bulge dominated. It has got old type of stars. So they don't. So these galaxies on the left hand side don't really have any fuel from which young stars can form, right? So the fuel to start with, atomic gas and also the molecular gas has been exhausted. Either it has been all used up, or the galaxy has gone through processes through which all such gas has been expelled out of it. Right. So when such a thing happens, a galaxy is primarily composed of old stars. And when we come to the right-hand side of this diagram, we see these beautiful blue galaxies with spiral arms, and they are blue because there's a lot of uh, uh, star formation ongoing in these galaxies, which also implies that there is a lot of fuel for star formation that is present in the galaxies, primarily cold atomic gas and the molecular gas. So the presence of gas in a galaxy is very crucial to how, what kind of stars that it can form, and then how it will look like. So that's the kind. So we are now building up the motivation to look at different components of ISM and the gas of the galaxy. So where is most of the gas in the galaxy that is distributed? So in the subsequent slides, we are going to now focus more on the late type galaxies, like the gas galaxies where the disk component is prominent. So mostly in these galaxies, ISM is also confined to the disk, but we do see a large range in the temperature. Temperature, the gas can be at temperatures of starting from 10 Kelvin. That's, we are talking about gas which is very cold, cold molecular gas. And then at the other end, it can be as high as 10 to 6 Kelvin. And here we are talking about gas which is ionized. So if we are talking about gas which has been photoionized by stars, then it will typically have temperatures of 10 to the 4 Kelvin. But then gas can also be shock heated and ionized. And in those cases, the temperatures can be as high as 10 to the 6 Kelvin. That's typically goes by the name of coronal gas in our galaxy. And similarly, similar to temperature, the density can shows also a very broad range, 10 to minus 3 to 10 to power 6 per centimeter cube. So overall, the ISM, interstellar medium, that we see in our galaxy is multi-phase. It has got molecular phase, it has got ionized phase, it has got also atomic phase, and it's also very clumpy and inhomogeneous. So the way we are now visualizing our galaxy through the slides which we have gone through is that there are the stars which are distributed. If it's a disk type galaxy we are looking at, they are mostly confined to the disk of the galaxy, especially the young stars. And then we have got this lot of gas, multi-phase ISM, which is also confined to the disk of galaxy, but it is a multi-phase medium. It is clumpy. It is inhomogeneous. There's a lot of empty space between stars, but it's not really empty. It is filled with all this gas and dust and also like magnetic fields and radiation field in between them. So how do we classify different phases of ISM? So as we know that hydrogen is the most abundant element, and this is then followed by helium, carbon, and so on. So what we do is that any phase of ISM, we classify it on the basis of the ionization state of the neutral hydrogen. So if most of the neutral hydrogen is actually in, or most of the hydrogen is in neutral phase, then we will call it the atomic phase. If it is in ionized phase, then we will call it H2 region or the H2 phase. And then if it is mostly molecular, then we will call it a molecular phase or the molecular cloud. And you'll be surprised to know that in our own galaxy, Milky Way, the and I'm going to give you some number that is by mass. By mass, if we look at 60% of the gas is actually in the atomic phase, and about 25% of it is 25% of the gas is in atomic phase, and only remaining 15% approximately is in the molecular hydrogen phase. So this is how gas is distributed. So most of the gas is in atomic phase. And next we are going to look at how is it actually it, 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 what are its physical properties and how it interacts with other phases of the ISM. So let's now focus on the atomic phase, which is what we wanted to focus on in these lectures. So neutral hydrogen. So let us just try to understand it at the atomic level. What is neutral hydrogen? Of course, from our perspective, it is most abundant. It's also the simplest atom. but it has got energy levels which has transitions from ultraviolet to radio wavelengths, and they all play a very important role in the ways in which we can observe it. So before we look into neutral hydrogen at the atomic level, let me also show you a few more pictures of how neutral hydrogen distributed in galaxies. So what you're seeing here on top is actually optical image of a galaxy, right? And in the bottom, what we are seeing is the neutral hydrogen component of it in this galaxy. So what are the two things? And these two images are at same scale. So what are the two things that we straight away realize from this? One is that H1 extent of the disk is actually much larger than the optical disk of the galaxy, right? And typically, if we statistically look at various galaxies in the nearby universe, we find that the H1 disk of galaxies extend by factor of 2 compared to the optical disk. So you have optical disk, and then there is H1 disk, which goes about a factor of 2 beyond that in diameter, right? So there's these outer regions of the H1 disk where no star formation taking place. And one of the things that we will look at in the second lecture is that why is it that star formation is taking place only in the inner portions and not in the outer portions, right? What is the reason? If atomic gas is present, it should be actually forming stars, right? And second thing that you can look at in this image is actually that there is a hole at the center, right? So if we just had the information only from these two images, we can jump to the conclusion that perhaps gas in the central region is ionized, uh, and that's why we don't see it. But that is not the case. What happens in most of the galaxies, including our Milky Way, that in the central regions, the most of the gas, the pressure in the disk is so high that most of the gas is actually converted into molecular phase, and that's the reason that we are seeing a hole at the center, because this image that has been made here at the bottom is made using H1 21 centimeter line, and we will talk about it in more detail in next few slides. So there's this 21 centimeter transition of neutral hydrogen atom, and when it sort of goes from higher energy level to the lower energy level, it emits a photon. So in this image, what we have done, we have looked at this galaxy, collected all the photons from this galaxy, and made this image. So this is how it looks like, and there's a deficit at the center, and that is happening because there's no neutral hydrogen present at here, so that we are receiving no photons from that. But if we look at it in, for example, carbon monoxide, which is a very nice tracer of the molecular gas in galaxies, we will find that there's a lot of molecular gas there. So this hole is not here because most of the gas is ionized. It is because most of the gas is actually in the molecular phase. And if we also look at it in the optical, this image is not zoomed in enough to show you the detail, but you can anticipate that there is a lot of vigorous star formation taking place in the central region. And then you can connect this back to what I was mentioning in the earlier phase. It is of the talk that it's the molecular gas which is the direct fuel for the star formation. So there's a lot of molecular gas present at in the central region. So there's a lot more star formation also taking place here. So these are direct connections that we can build between different phases of ISM and the ongoing star formation in the galaxy. But then there is another aspect of looking at neutral hydrogen from galaxies. This image that is presented on the right-hand side is the neutral hydrogen image of a galaxy group. And on the left-hand side, you can see the optical image of this galaxy group. So if you look at just the optical image of this, you will find that, I mean, this is a boring group of galaxies. Like there is three different types of galaxies, but there's nothing happening between them. What is interesting about it? But if we look at it in neutral hydrogen, again, you will find that each one of these galaxies and both left and right hand side images are at the same scale. So you can see that like the neutral hydrogen actually is extent much more than the optical extent of these galaxies. And not just that, there is actually a lot of gas present between these galaxies, and we can from the neutral hydrogen image clearly make out that these galaxies are actually interacting with each other, right? And this is a process which plays a very important role in the evolution of galaxies. So there are two aspects of galaxy evolution. One is that how galaxies acquire gas uh, uh, from circumgalactic medium, which is the medium just outside the galaxy, and can convert it into stars. That's one. And second being that how they interact with the other galaxies in the vicinity. These essentially represent two processes through which galaxies evolve. And if you look at this one, H1 was extending far beyond and it formed a direct connection between the stars that are forming in the galaxy, and especially if we put together with the molecular gas phase also. And in this case, we can see that there is this ongoing interaction between the galaxies, which we can see very clearly in neutral hydrogen, but not at all in if you look at only the optical images. So this is an extreme example. There are cases in which optical morphology also is distorted, but often since H1, you can uh, appreciate that since H1 extends so much more than the optical extent of the galaxy, any interaction that a galaxy has with its intergroup medium, because it is traveling with a certain velocity, or an interaction with its neighboring galaxies, it will leave its imprint much more in the H1 disk of the galaxy, just because of the simple reason that it extends much further. So it presents much more cross section here, right? So a neutral hydrogen observations of galaxy is a very effective way of understanding galaxies and their evolution. This is another example of it. What is it that we can do? Because since this is a spectral line, H1 21 centimeter being a spectral line, not only we can look at the distribution of the gas, but we can also look at the kinematics of it. So right hand side presents the kinematics of the galaxy, and here you can see that like it presents a systemic rotation. So you can see that what we are learning from here is that the gas is actually the disk in this galaxy is actually rotating. On one side we see blue shift, on the other side we see very nice red shift. So now let's after this digression, let's go back and try to understand what is it that we can uh, uh, learn from the neutral hydrogen as the simplest atom. So these are the what we're seeing here are the principal quantum numbers. Like, so we are all familiar with different transitions that can take place between them. For example, Lyman alpha series is there, which is represents the transition from higher energy states to n equals to 1. Then to n equals to 2, we have Balmer series, which comes in optical, Paschen, and so forth, right? So these are the different transitions through which we can learn about Lyman alpha. So Lyman alpha, when it's so hydrogen when it's ground state, one of the very simplest transition is that we can look at is from the n equals to 2 to n equals to 1. That is 2p to 1s transition. That corresponds to Lyman alpha transition, and it has a wavelength of 1215 angstrom, right? So it comes in ultraviolet, right? So let me repeat this because we are going to make some direct comparison with other transitions of neutral hydrogen atom. So Lyman alpha corresponding to 2p to 1s actually has a wavelength of 1215 angstrom, which is in ultraviolet. So it's only at when we look at objects which are at redshift greater than 2 that it actually gets redshifted into optical band. But you may ask that what about these different transitions, H alpha, for example, Balmer series, which is in optical? Can we use this to look at neutral hydrogen? Yes, that is correct. We can look at use these to look at neutral hydrogen, but these are actually corresponding only to the recombination lines. So they are sensitive to a gas which is in the ionized phase. Okay, so that's the major difference. So since we are interested right now looking at the atomic phase of the gas, let's focus only on the laminal. That's the 2p to 1s, right? But one more thing that happens, and that is like if we also consider the finer hyperfine transitions of a neutral hydrogen, then the ground state of it actually is split into two states. It's not just one state; it's split into two states, and and this splitting is called hyperfine splitting, and it arises due to the interaction of magnetic moment between electron and proton. And what happens in this case is that when electron and proton spins are parallel to each other, then there is it corresponds to a higher energy state, and when they are anti-parallel to each other, it corresponds to a lower energy state. And the presence of such a line was actually theoretically predicted by Heinrich van der Hulst in 1944. And this is something which he carried out, this work he carried out as part of his PhD thesis in supervisor Jan Ort. And he realized that if a transition of neutral hydrogen existed, then it would be very useful probe to look at neutral hydrogen in our own galaxy. And at that time, the ambition was to look at it in our own galaxy, but of course, like, it is very easy to extrapolate that such a probe will be useful to look at not only external galaxies but also for the early stages of universe, which is what it is used for now. For example, epoch of reionization experiments that are targeting to look at neutral hydrogen at very high redshifts in the universe. And as soon as it was predicted in 1944, a set of experiments were carried out in USA. That was by Iwan and Purcell. Then Ort and Muller carried out a similar experiment in Netherlands. Not experiment, I should call them observation. They set up some of the first telescopes designed to detect neutral hydrogen from our galaxy, and Christensen and Heinemann in Australia. So these three groups almost simultaneously, Ewan and Purcell were the leading ones, but these three groups within a year of each other actually made the first detection of neutral hydrogen from our galaxy. So that was a very major milestone. And what this 21 centimeter line does, as I was saying, that ground state is split into two energy levels, and if we can represent them by a simple two-level system, then let's call n equals to 1 or n equals to 0, n equals to 2 as these two states, then energy separation between them actually corresponds to a frequency of 1420.405752 megahertz. That's the energy separation that is corresponds to, and in wavelength units it corresponds to 21 centimeter. That's why I have been till now calling this line by the 21 centimeter line, like that. Now there are a few very interesting things for us to relate or compare this transition to Lamin alpha, and this is something which all of you actually through your atomic physics have come across, but let us try to make these connections more apparent and direct, so that you can so that all of us can appreciate that why this line is so different and special with respect to any other line that we come across. And we will pick Lamin alpha and 21 centimeter. So let's first focus a little bit on 21 centimeter. So if we have, let's say, a two-level system like this, then we can represent the number of atoms in excited state, let's say level 2 and level 1, through this Boltzmann law, right? And G2 and G1 here are the statistical weights of this. And in the exponential, we have h nu by kt. T is the temperature, right? So h nu by k here, if we estimate what this value would be for 21 centimeter line, if you plug in nu here as like 1420.405 megahertz, and h and k are just the fundamental constants, if you put them, we find that this value is actually 0.068 Kelvin. Okay, so and T is the temperature. So we are talking about astrophysical conditions. So if you look at neutral hydrogen in interstellar medium of our galaxy, the kind of temperatures that we are talking about is like at least 10 Kelvin. Right? If you go back where I was talking about the range of temperatures that we see in our ISM, we see temperatures of say 10 Kelvin or so, and then it can be as high as 10 to 6 Kelvin. And if we are talking about only the atomic phase of the ISM, where such a line would be observed from, then in that case, we are talking about temperatures of tens of Kelvin to, let's say, few thousand Kelvin. So if we put h nu by k here of 0.068 Kelvin and typical temperatures of, let's say, 100 Kelvin that we see, then this quantity is just reduced to the statistical weight that we see here, right? Because we can approximate it by 1 minus h nu by kt, and h nu by kt being very small, this is then just simply G2 by G1. And the excited state of this hyperfine transition is actually a triplet state, which means that G2 is equal to 3, and ground state is a singlet state, so G1 is equal to 1. So N2 by N1 is actually 3, right? So what this implies that the excited state, so most of the atoms, like if I have like a certain number of atoms, then 3/4 of them actually will be in the excited state. That's very bizarre, actually. It does not happen. In case of Lamin alpha, if you look at, most of the atoms would actually be in the ground state of hydrogen. They would not be in the excited state. And why that is the case? And that is something which is related to the Einstein's A coefficient, which actually represents the spontaneous transition probability from the excited state to the ground state. So just to quickly revise, right? If we have a two-level system like this, then there are several ways through which it can go from ground state to excited state. And if you're talking about only radiative channels, then it can actually have a stimulated absorption through which it can go from ground state to excited state. Then from the excited state, then it can come through two channels, spontaneous and stimulated, right? Which are represented by Einstein's A and B coefficient. Right. So I'm assuming that basic concepts like these have been covered in lots of other lectures, but if that is not the case, then please have a look at any of the basic physics book, or look at something like Ribicki-Lightman radiative processes. First chapter of it would give you an idea of like how the Einstein A and B coefficients can be used to represent radiative transitions between these two states, and then how Einstein's A coefficient is then related to the lifetime of the state. So if I take the 21 centimeter line, Einstein's A coefficient is for this is actually 2.9 into 10 to the power minus 15 per second, right? That's the kind of transition probability that it has. And if I convert this, and the reciprocal of this is simply the lifetime of the state. If I convert then this turns out to be 10 to 7 years. Now you have been attending lots of lectures, and you will find that in even in for astrophysics, 10 to 7 years is actually a very, very long time. So what happens in this case, and for comparison, if I tell you that what is the Einstein A coefficient for 2p to 1s laminal for transition, you can look at any of the atomic physics book. It is actually 10 to the power 9 per second, right? So the reciprocal of this, you can find that it is like a nanoseconds that we are talking about in that case. So this is the reason that if I'm looking at in case of hyperfine states, even without doing anything, right, in ISM or any realistic situations, most of the atoms are in actually the excited state. But when we are looking at 2p to 1s lamellar for transition, Einstein's A coefficient is transition probability is so high that most of the atoms, as soon as it goes to the excited state, it comes to the ground state. So they will be in the ground state. So these are very interesting implications that how we can observe a neutral phase of the ISM, or that of the ionized phase of the ISM. But let's stick to atomic phase for now. So another thing that we can ask is that if there are these two different states, then atom can, through various radiative processes, can go from ground state to excited state and vice versa. But then there can also be collisions that can be taking place between these different atoms. And do they play a very important role in affecting the level populations in this case? So the answer is yes, and answer is yes for particular special reasons for 21 centimeter line, because if I just estimate what would the collision cross section, let's say there is a hydrogen cloud at a certain temperature, then I can take the cross section as n sigma, and we can just for back of the envelope calculation set sigma to be the radius of the hydrogen atom, and we can take the typical densities of the atomic phase to be 1 per centimeter cube. And later I will show you that how some of these things are estimated and how these are known. And from this, I can estimate something what is called the mean free path, which is the distance that a particle or an atom in this cloud would travel before it collides with another atom, right? And that turns out to be 10 to 15 per centimeter square. And since I know that the temperatures that I'm talking about are like a few hundred Kelvin, and I know that it's in thermal equilibrium, so if I can use Maxwell-Boltzmann distribution and estimate what is the typical velocity, that turns out to be this. And so I can estimate what is the typical time between successive collisions, and that turns out to be simply 200 years, right? That's so what does it mean? On its own, probably you can say that it means nothing, but you can we need to put this in the context of the lifetime of the excited state of 21 centimeter transition, that is 10 to 7 years, right? So you can see that the atom stays in excited state for so long that collisions can actually play a very important role in actually affecting the level population of that. By collisions, it can actually come down to the ground state of it, right? And this wouldn't happen ever for laminal for transition, because the lifetime there is so short. So these are some of the peculiarities of 21 centimeter line with respect to the any other transition that we look at it in optical and ultraviolet, right? These are the kind of comparison that we're making are fairly generic here. So thus collisions actually play, so what we learned from this, that collisions can play a very important role in determining the level populations, that is spin temperature. So I have introduced a term here, new term here, spin temperature. What does it mean? So if I have any two levels of uh, an atom or a molecule, I can write this equation, right? Regardless of whether it is in thermodynamic equilibrium or not. So N2 by N1, G2 by G1, and in a very generic sense, this T is called the excitation temperature. And what does this represent? This represents nothing but a simple term through which I am a nomenclature through which I am representing the level populations N2 by N1 for this two level system. If it is in thermodynamic equilibrium, then this excitation temperature would actually correspond to the kinetic temperature. Otherwise, it will not. So let's keep. So this is a very important point, that we can actually use this equation to represent the level populations, call that as excitation temperature. But this excitation temperature need not be actually the kinetic temperature of the cloud at all, because and it will depend on the processes that influence the level population. Only then this temperature can be actually equivalent to the kinetic temperature of the gas. And we will look at it, what are those different things can be. But for that, let's have a quick overview of the kind of radiative transport we are talking about here. So the what I want us to visualize is that there is a neutral hydrogen cloud, and there is a, let's say, a bright star behind it. And we can also put this in an extragalactic scenario where this cloud could be a galaxy and the star could be actually a quasar a distance, and this experiment will still hold. And what we are trying to do is that if there is this star, the radiation from this travels and it will interact with this cloud in between. Now there are two possibilities here, that some radiation may get added to it, which is represented by this second term here, this in the differential equation J nu, that's the emissivity of the cloud. And another thing that can happen, that the incident radiation that is coming in, a part of it will get absorbed. So there's this first term with a negative sign presented, right? So di nu by ds is representing the change in specific intensity per unit path length. Again, I'm quite sure that you have come across this many times, but this is the simple radiative transport that takes place. And I can write this in the units of what is called as the optical depth, right? And optical depth is defined as like alpha nu being the absorption coefficient and ds being the path length there. So even if some of you are unfamiliar with this or not following this algebra, again, I will but are interested to know more about it, you can look at the first chapter of Ribicki Lightman. But what we are trying to do here is that trying to determine how the radiation as it propagates through an intervening cloud gets modified. And you can solve this differential equation very easily, actually. And again, like I will say that you can go to Ribicki Lightman, or you can follow the steps here. And simply what we do is that we multiply both sides by exponential of minus tau nu, which is optical depth, and then you can integrate this, and you get this integral equation here simply. So what is the first term representing here? First term representing here the incident radiation which got absorbed. So this is pure absorption. And then this second term is representing the portion which is actually a contribution by emission from the cloud and also the self-absorption. So that's what it is representing, right? So if you have not followed the algebra behind it or the differential equation, just keep this in mind, that the first term is pure absorption and second from the cloud, intervening cloud, and second term is emission and absorption as modified by the by this cloud itself. So if no emission is present from the cloud, then only the first term will be existing, right? And if there is no source star or agent in the background, then the first term will go away, only the second term will exist, right? That's quite obvious once we identify these through this. So if I take a cloud which has uniform properties, then this integral becomes even simpler and I can solve it, and this is what this term becomes, right? So now let us try to understand what would happen to this cloud kind of experiment that we have set up in this case. One more approximation that we can do is that at radio wavelengths, we can use what is called a Rayleigh-Jeans approximation of the Planck equation, and we can write this specific intensity actually in the terms of temperature. and we call this brightness temperature. So I'm introducing another term here. This is brightness temperature. But again, this is not to be confused with the temperature or the kinetic temperature of the cloud at all. I'm just rewriting specific intensity in terms of a temperature using the Rayleigh-Jeans approximation. And again, there can be situations when this temperature may become equal to the kinetic temperature of the cloud, but in general not. So let us not confuse the two. So if I rewrite this, then this is the brightness temperature of, let's say, background star or the AGN. Then this is the incident radiation on the cloud. This is first term which gets modified. And this T cloud is the temperature of the cloud. And the second term is representing emission and absorption that is happening with respect due to the cloud that is present between us and the background star or the quasar, right? So what is it that would happen in this case? So there are, so this, we rewrote this in the units of temperature because it allows us to appreciate certain things very easily. So we take this same equation and we subtract from both sides this incident radiation TB0 on the cloud, right? So this part right hand side gets modified like this. Okay. So this is so what does my left hand side represent in this case? It represents the deviation with respect to the incident radiation on the cloud, right? So this deviation would appear as emission if T cloud is greater than TB, right? Then this will be positive definite, and in that case that will be appear in emission. And if this is actually less than that, then it will actually appear in absorption, right? That's a simple thing that we wanted to understand. So that if the cloud is at a temperature which is more than the brightness temperature of the background source, then we will see it in emission. But if it is lower than that, then we will see the cloud in absorption. And if it actually is both the things turn out to be equal to each other, then in that case, actually, I will not see the presence of cloud at all, right? Because then this whole term will actually go to zero. So this is starting from this. Let us now try to understand a little bit more about what happens to the 21 centimeter line in different physical conditions in our ISM. So if you recall, we had defined a quantity called optical depth here, right? And this is related to the absorption coefficient, which is here. This is, you can think of it as a probability of absorption of a photon of a particular frequency. So what happens? So this is related to Einstein's B coefficients in this way. We can, what we are writing here, this is the stimulated emission corrected for stimulated absorption. This is what it is, and this is related to this B21 and B12. These two Einstein coefficients are related to each other through statistical weights of the two states simply, and this B21 is related to the Einstein's coefficient again through some simple fundamental constants. So what basically I'm trying to tell you is that the simple term here is can be rewritten very simply as N1, which is the number of atoms in the excited state, in the ground state, B12, and h nu by kT. And now if you recall that if we don't do anything for 21 centimeter line, and even then N2 by N1 is actually 3, that most of the atoms are in excited state. This is the basic principle of it, right? So then this alpha nu or the pi nu is related to total number of atoms and T, which is the spin temperature. So what this is telling us that the absorption coefficient or the optical depth, absorption probability, is related to not only the number of atoms which are present, which should be obvious, which is what happens in every possible case. This is true for laminar alpha transition also. But in case of 21 centimeter line, it is also actually depending on something called the spin temperature, which need not necessarily be the kinetic temperature in general. Right. So if I take a optically thin cloud, what is the meaning of optically thin cloud? Optically thin means that optical depth is actually much less than 1, right? And I'm considering only a cloud, so there is no background source. So which means that I can remove this second term. So there is no absorption, right? So I'm just taking the second term from this equation. And if I put this here, so Ts 1 minus E minus tau. So then this is actually, again, I know that h nu by k is very small, tau is very small here. So I can write this as Ts tau nu, Ts multiplied by optical depth, and this is Nh by Ts. So you can find that actually if the cloud is optically thin, then the brightness temperature of it or the emission that I receive from it is actually dependent only on the number of atoms that are present. So, which is the conclusion here that for an optically thin cloud observed in emission, spin temperature is of no consequence. And this is a very important conclusion. These two things, the fact that absorption is depending on both the number of atoms that are present and also the spin temperature. And what does spin temperature represents? Spin temperature represents the level population of excited and the ground state corresponding to the hyperfine splitting, right? Whereas like when I am talking about emission, it depends only the total number of atoms that are present. And since it is optically thin, the simple picture is that any atoms that goes from excited to the ground state radiates a photon, and I will receive that photon, right? Because it's optically thin. Since it's optically thin, this photon is not going to get absorbed within the cloud. So, from simple atomic physics, it's fair to anticipate that in such a scenario, the number of photons that I receive will be directly related to the total number of atoms which are present somehow with some proportionality constants. And then using that, I can straight away derive total neutral hydrogen content of the galaxy or the H1 mass of the galaxy. So this becomes, and this is something which is very, very difficult to do with any other transition, like let's say Lyman alpha. In that case, you cannot relate it directly to the number of atoms that are present. So 21 centimeter line becomes a very nice or useful probe to measure the H1 content of galaxies, which, as you were discussing initially, that it's so crucial to understand how the galaxy evolution will take place. But in the next slide, we also look at it can also give us very crucial information about the thermal state of the gas that is present in the galaxy. And this is an experiment or observations for our own galaxy. What each of these plots, in each of these subplots, what we are seeing here, there's a profile which is looks like emission, and there's a profile which looks like absorption. So they're nothing but emission and absorption. And what we have carried out in this case is actually an experiment of this type, that we look at a certain region of our galaxy, but we pick a cloud such that there is actually a source in the a bright radio source in the background. So we are seeing a part of cloud in absorption. And then if I move my sight line to the cloud slightly away from this radio source, then this first term will not be present. Then I will be seeing only emission, right? So there are two things we have done here, right? So for each cloud, each direction in the sky, I am looking at a sight line which has a background source behind it. So in that case, I will see this absorption here for sure, right? Because that radio source is very bright. It's an AGN, so its brightness temperature is much higher compared to intervening cloud, which will have a temperature of a few hundred Kelvin, right? And background source will have temperature of millions of Kelvin and even more. And then when I am looking at a cyclone slightly away from the radio source, then I will not have any absorption because there is nothing behind. I will see this cloud only in the emission, which is this second term that I am talking about. Right. So you will say, what's the big deal actually about it? Like, this is that equation. This is what we anticipate mathematically, and this is what we are seeing. But if you carefully examine these two clouds here, right? These two plots, sorry, emission and absorption. If you compare for each of these cases, you find that emission is actually present over a much broader range. It's much wider here, right? Whereas the absorption you see in each of these cases is actually confined to much smaller velocity range. So x-axis here is velocity, right? So what's happening that any cloud that I'm looking at will be at a certain temperature, and it will also have a bulk motion. So as a combination of this temperature and the bulk motion, the absorbing atoms or emitting atoms in this cloud will have some relative motion with respect to observer, in case us, or a telescope. So this line will have a certain spread with respect to that. That's what we are seeing here, this spread. But in addition to that spread, we are also seeing that absorption is actually confined to much smaller velocities compared to emission. So let's go back to this. What we learned in the previous slide, that absorption is actually proportional to not just the number of atoms that are present, but also to inversely proportional to the temperature of the gas, spin temperature. which in some cases actually can be a good representative of the kinetic temperature. So for now, just for this particular experiment, let us consider situation that spin temperature, we say that is a good representation of kinetic temperature or the thermal temperature of the gas. This is just to simplify our discussion for now, right? No loss of generality here in this case. So this, if we take here, you would say that in emission I am seeing all the gas that is present, right? Because this does not depend on the temperature at all here. But when I am looking at in absorption, I am looking at gas which is actually colder. So there exists also a portion of the gas which I am not seeing in absorption, and I am not seeing in absorption because it is at a warmer temperature. Because absorption strength is inversely proportional to the temperature of the gas, right? So this was the set of first observations through which it was realized, it was understood, it was proven that atomic gas is present in our galaxy. 60% by mass, the total hydrogen in our galaxy, Milky Way, is atomic. But it is not all at the same temperature, actually. It is at least at two distinct temperatures. And these temperature, two phases were then called as cold neutral medium and warm neutral medium. So cold neutral medium corresponds to a gas phase, which is at typically 100 Kelvin, and warm neutral medium is the gas which is at temperatures of about a few thousand Kelvin in that case. So there is this neutral hydrogen, which all of it which we are seeing in emission, but since a large portion of it is actually present, is at a much higher temperature, I'm not able to detect any absorption with respect to it, right? Absorption with respect due to this is actually buried in the noise. So this was the discovery of the two-phase medium in our galaxy. So this it is anticipated that such a two-phase medium exists in other galaxies also. So after lunch, we have a lecture in which we will look at the physical properties of this two-phase medium in little more detail, and also we will look at what is it that we can or have learned about neutral hydrogen in external galaxies, right? So just to finish, what I'm presenting here is the neutral hydrogen map of our own galaxy, the Milky Way, right? So the color scale here corresponds to the intensity of the neutral hydrogen emission. So it's directly, as you know, that since especially in the places where it is optically thin, it directly corresponds to the total amount of hydrogen that is present. And you can see that the most of the bulk of the hydrogen is actually confined to the disk of the galaxy. But then there is also low column density hydrogen, which is actually outside the plane of the galaxy. It has been thrown off the plane of the galaxy through various physical processes. And some of it may also actually be falling back. Whether it is doing that or not, how do we know? Because since it's a spectral line, we can also look at the kinematics of this gas. So there's various details of this, which we will look at it in the second part of the uh, talk. And I'll just finish with this slide here. I will not talk much about it, but this is just to close the loop with which we started, that although we are focusing on the neutral hydrogen phase, but we have to keep in mind that all these different phases of ISM are interlinked with each other. Top we have ionized phase, coronal gas, and as we come down here, we have got the molecular phase from which actually stars are formed, and there is this whole range of physical processes through which gas can actually go from one phase to the another. And so left hand side is all cooling and or going from high energy or warmer to cooler and less ionized phases, and the right hand side you can see the processes which correspond to actually the ionization of it, right? So for now we will stop here, and then let's see if we have got some questions. I'll stop sharing my slides for the moment so that I can look at various questions if there's something that has come in Google chat. uh, so I also see a raised hand, but let me quickly answer this question which is there in the chat because it's very brief. It's talking about, please repeat the percentage distribution of molecular, atomic, and ionized phases in Milky Way. How do we reach at these estimates? So yes, so if we these percentages, if we look at it by mass, then they would correspond to 60% for atomic phase, approximately 25 or 23% for the ionized phase, which was H and Roman numeral 2, and then 15% of it is in the molecular, remaining of it. And how do we come to this? Actually, we have to measure it actually through observations. And in this lecture, we saw how we can use 21 centimeter line to measure actually the total hydrogen mass content of the galaxy. That's how we know about the H1 phase. And then if you want to look at H2, molecular hydrogen, that's most effectively done through observations of CO. So observations of CO, its ground state transition CO120 would come at approximately 115 gigahertz. So that's high frequency, high radio frequency observation. That's where it will be. And for ionized gas, this is done through observations of recombination lines, which will come in optical. That is like Balmer line, for example, H alpha. It will be a very effective tracer to look at ionized phase for this in the galaxy. So looking at these three, we can determine how much total mass is there and how it is distributed in different phases. This is how it is done. So now let's look at, so we have got two raised hands. So first is Pushti Shimankar. Please unmute and ask your question.
Hello, sir. Sir, am I audible?
Yes. Yes, you're audible.
Sir, actually, I have two questions. First, regarding the temperature, which you said that optically thin cloud in emissions. So, if we take the optically thin cloud in absorption, then what will be the result?
So if it is an absorption, it will be, you will see it in absorption, because the reason whether it will be in emission or absorption will depend on what is the temperature of the cloud. In this case, spin temperature of the cloud with respect to the brightness temperature of the background source, right? So that will determine whether it's in emission or absorption. But if optical depth is small, then only thing that will happen is that absorption will be weak. And if optical depth is large, absorption will get deeper. That's all that will change, right? Because optical depth is simply a measure of the strength of absorption.
Okay, sir. And sir, one more question that if we talk about it after billions of years, Andromeda Galaxy and Milky Way will be collide. So, is there any change of this atomic gases in our galaxy?
So this kind of yeah, so let's talk about it in the next lecture, because there we will talk more about how neutral hydrogen of galaxies get affected when they interacted with each other. I'm going to present a lot more information and examples of it. So let's talk about it. It's a very interesting question. Let's get to it in the next one, because we will have some background discussed with respect to it. Okay.
Okay, thank you, sir.
Okay, so next is Shlok Shah. You have a question.
Yes, sir. Am I audible?
Yes, clearly.
Okay, sir. Actually, I wanted to ask when you explained about neutral hydrogen line, that 21 centimeter line, you mentioned figures like 10 to the power 7 years or something like that.
Yes, yes.
What those figures signify?
So that was what was 10 to 7 year actually. That is corresponding to the lifetime of the excited state, which means, so it is simply a reciprocal of the Einstein's A coefficient, right? And Einstein's A coefficient represents the transition probability, spontaneous transition probability from the excited state to ground state, right?
Yeah.
So that is just the lifetime of the state, which means that if an atom is in the excited state, it will remain in that for 10 to the 7 years, right?
So, sir, won't it?
So such a long time actually. So the significance of this was that it can actually, through collisions, the level populations can get affected between the hyperfine states, because the time between collisions is only 100 years, right? So this means that this atom which goes into the excited state can undergo a collision with another atom and lose energy to it and come to the ground state through collisions and not through the radiative de-excitation, right? So as a result of this, what happens that collisions play a very important role in maintaining the level population. This becomes very important in when the densities of the clouds are very high, because then the collisions are frequent enough, then actually the level populations or the spin temperature can actually become directly related to the kinetic temperature of the gas in that case, right? Because for anything to come into thermodynamic equilibrium, it is through collisions, right? That's the physical process that we are looking at, isn't it? Let's say if I take a cloud of, let's say, I consider, let's say, electrons, right? And if I uh, introduce an electron with another certain energy, right? Maybe a very high energy or a very low energy, right? Then this cloud is at a certain temperature, right? This hydrogen or this electron, as it is introduced into this cloud, will actually share its energy with the remaining electrons or particles which are there, and that is through collisions, right? And it will come to the same thermodynamic equilibrium or the same temperature, which is the representative of the cloud. So collisions play an important role in determining whether the system that we are looking at will be in thermodynamic equilibrium with the other species or not, right? So the comparison of uh, the two numbers, that the lifetime of the excited state is very large, 10 to 7 years, but the time between successive collisions is only 100 years, implies that the level populations of the two hyperfine states, in if the density is high, can actually be governed by collisions, right? And in that case, spin temperature becomes a direct measure of the kinetic temperature of the gas that is in the equilibrium, thermodynamic equilibrium with that, right? That's the significance of that number.
Okay, sir. Thank you so much.
So I don't see any further raised hands. I will quickly look at if there is something in the Google Doc sheet. So there's nothing in the Google sheet. So you all have done very well. So I think it's very effective that you ask question live here or put it in the chat. That's much more easy to manage. That's we try to follow in the next lecture also. So this is now we are 2 minutes past schedule time. So we stop now if there are no more questions. And I'll see you again at 2:30. That is right.
Thank you, Neeraj. Thanks for the nice lecture.
Okay. Thanks. Thanks.